Basins, new insights from Lola data.
Thank you very much. And if you could turn the lights down a little bit too, I appreciate it. So a really important thing in terms of understanding the thermal evolution of the moon is volcanic flooding. Where did the magma come from? How did it get out on the surface? How is it related to what's going on in the interior? And one of the key things about the Lunar Reconnaissance Orbiter is giving us incredible amounts of data to be able to address this question. And key questions that are associated with this have to do with, in fact, what's the total volume of volcanic deposits that gets to the thermal evolution? What's the onset and termination of volcanic activity, issues that have faced us for eons? And what's the volume as a function of time? That's the flux. How is it related to impact basin formation? Recently, people have described scenarios in which impact collapse induces convection and produces upwelling and melting over the course of hundreds of millions of years. We can test these hypotheses now. And what's the distribution of early volcanism? Cryptomare, non-Mare volcanism, and so on. And how is it related to the tectonics? Well, the instruments associated, particularly the Lunar Orbiter Laser Altimeter and the LRO camera that Mark just described, I'm going to focus on the Lola instrument because it's given us some really amazing data, and the LROC has complemented this beautifully. So how do we look at this? If we go back 1 second to this image here, most of the kinds of things we see here, all these flooded basins are on the near side, like Imbrium classically. Well, of course, we know that the Oriental Basin, from the moment it was discovered, is in fact a huge impact basin, 930 kilometers in diameter, which is not flooded very much at all. It has a thin mare in the middle, but in fact, it's essentially a laboratory for the study of how basins start out and how initial flooding works. So if you take a look at this perspective view, we ask the question, what can we learn about early impact basin filling from Oriental? And in fact, Jennifer Witten has just published a paper using LROC data, using using LROC data, using Lola, and also ImCube data to, in fact, assess the geology of the early Mare filling of this and understand how it relates to the basins as a whole. What she's done, in fact, is to look at each one of these Mare deposits in here and then take a look and go in and look at the impact craters. Yellow craters here excavate Mare material, white craters excavate below that into a northacitic material. And using the depth diameter relationships here has been able to build up essentially an isopac map, which in fact shows that most of the Mare here is less than a couple of hundred meters. Using the same approach, she's been able to actually work through and date these things as well. And what you'll see here is 1 second is 100 million years, my usual rate. And you can see here that Mare Oriental itself comes in early, and essentially there's not a lot more volcanism that occurs inside the basin, but with time we see Mars Virus and Autumni begin to fill up, and this is quite a wide range of Mare basalt ages here, till ultimately less than a couple, 3 billion years ago, we start to fill in the outer portions here, and the last is at about, come on, you can't hurry these things up, they are what they are, 1.66 here in the outer edge here. So this is really interesting because if we compare this to the relationships to other basins, here for the near side as a whole, we see in blue the distribution. There's a wide range of ages. It peaks at about 3.3 to 3.7. And note in yellow, Oriental, it too has a wide range of ages, and it peaks at about the same time, but it's much less abundant. So this is really important because it tells us that there's nothing special about the relation to the impact basin itself, and we're talking about broad similarities in the near side and the western limb that don't seem to have anything to do with the formation of the basin itself, but rather is a broad-scale lunar thermal evolution. This is really important for distinguishing ideas about the origin of Mare basalts, which she talks about in that particular paper. Well, what was the onset in this area? Well, of course, we know that there are cryptomare on the near side, and indeed in the Oriental area. Oriental impacted after Mare volcanism had started. This is well known. The person who just asked the question, Irene Antoninko, has just, in fact, done a series of studies in this area here, looking at dark halo craters and the depths and significance of the cryptomare. B. Ray Hawk, Schultz, Budis, and others have also done this. And you can see there's several areas, including the floor of Schiller-Chicard, which in fact were sites of Mare volcanism prior to Oriental forming itself. So we can actually now go in and look at these in more detail with the topographic data to get an idea of the flux there as well. Now, we can also essentially ask the question, how do fresh impact basins fill? Now that we have this incredible topography, we can work through in 500-meter increments and flood these basins to understand how, in fact, these things essentially fill, and volumes. The volumes that we can get really are critical to assessing what's going on in the more filled basins. So we see two stages of fill, sort of a hockey puck, a thick, small radius interior, And then if you go from here to the rim crest, there's another few kilometers, in fact, where a larger radius, but a plate-like distribution. So now we can use this information to help model the loads in the other basins. Well, what about other kinds of effects that we can look at as well? What about flooding in the Highlands? What about places like the South Pole Aitken Basin? Another thing we were able to do with the LOLA data is to actually map every crater larger than 20 kilometers on the surface of the moon in a paper published in Science last year. We presented this information, and here it is in N20, the number of craters larger than 20, in a moving average across the surface. And you can see the Mare are young, Oriental is young. Some of the basins here we know to be young from Don Wilhelm's work, in fact, are still seen. We can ask the question, what's going on here with the distribution in the South Pole Aitken Basin? So if we plot the distribution of craters 20 kilometers in diameter inside the basin, within the basin, and outside, we can compare the two to see if they're similar. And what we see here in essentially incremental frequency, cumulative frequency, and R-plot space is that South Pole Aitken Basin has a comparable or higher density of craters greater than 75 kilometers, but at sizes of 20 to 64, SPA has fewer craters than outside the basin. Well, how do you do that? They both are probably, should be saturated on the basis of the ages, but something's going on in terms of this particular discrepancy, okay? So this is not advancing, but we're going to be patient. There it goes. So what's going on here? Well, there's several possible processes. We could look at impact craters, proximity weathering. That means if you're standing, you have a side view of an impact crater, you're going to get covered with ejecta if you're close enough. That's proximity weathering, okay? So we have possibilities of Oriental and Schrodinger in the basin, volcanic resurfacing. Maybe Mare deposits fill these up, probably not based on the ages, but maybe there's crypto-Mare or early Mare, non-Mare volcanism. And we also have lithospheric processes. Obviously, since this is a big basin, it could be sampling a lithosphere that, in fact, at the time was thinner, craters superposed on top of that, maybe viscously relaxing, losing their rim heights, etc. Or it could be the devil in the details, some or all of the above, okay? So that's, how do we deconvolve this complex signal? Well, we can start looking at the beautiful topographic data from LOLA and start superposing things. And when we start out, we can see the craters greater than 20 kilometers. We can see 20 to 60, all craters greater than 20, 20 to 64, and you start to see some discrepancies in here. But when you put the Oriental Basin ejecta as mapped by Don Wilhelms, Jack Macaulay, and colleagues at the USGS, you can see that it isn't really seemingly doing the job here. On the other hand, when we move in, we can look at interior crater basin ejecta. Here, like Schrodinger, that also doesn't seem to be doing the job. And we can look at things like the Mare, is shown in red here. These are all mapped by Desiree Stewart-Alexander and other colleagues at Wilhelms, etc. And you can see here in work by Eileen Yanks that when you map out all the Mare patches here, and here's a tedious table, if you're ever interested in the volumes and relationships, believe me, it's in the literature. And you can see here that, in fact, there's not enough Mare, so maybe there's crypto-Mare. So how do we look at this? Are there units in the terrain here, like the Imbrium plains, that might actually be evidence for crypto-Mare, older volcanic deposits that might be doing the job? Well, how much lava flooding is required to remove this part of the crater population? Again, enter the LOLA data. We can sit here, we could do the same flooding things at 100-meter increments, and just watch these craters essentially disappear here as we're flooding it in 100-meter increments. And you can see that they're pretty much going away. And by the time we get to here, which is about, keep with me here, it's coming. You can see the flooding sequentially here, okay. About 2 kilometers of Mare basalt flooding can largely obliterate evidence of the 20 to 50 kilometer crater. So maybe this is what's going on. Maybe we do have crypto-Mare in this area, not over the whole basin necessarily, but in parts that are producing this variation in the flux. We can also look, the LOLA data are just incredible because you can look at the multiple scale lengths of roughness here, and actually in a paper by Rosenberg et al., you can see evidence for smoothing in these areas that are also potentially consistent with the presence of crypto-Mare. So the bottom line here is we think that at least in part of the area here, crypto-Mare may in fact be an element in changing the crater size frequency distribution to that observed that we measured using the LOLA data in the first place. So this is something to be tested because, in fact, we want to go look at the viscous relaxation. Maria Zuber has some students looking at that at MIT at the present time. So we can use this information too, again, using the LOLA data to sort out these various sources of variability. So again, getting back to some of these basic questions here, we're really getting to the point where we can start to address many of these questions. I've tried to give you a potpourri, if you will, of examples of how you can use the MOLA data and crater size frequency distribution in populations and flooding, And we're getting to the point now where we can really take a look at the details, but we've been looking here just in the Maury deposits, okay, in the basins, in the big basins themselves. What about the highlands? I just draw your attention to a paper tomorrow by Jennifer Witten, in which she will talk about looking at 3 heavily cratered terrains here, heavily cratered terrain in the highlands, the Hertzsprung Basin, and the central region here at the edges of the Nectaris Basin. And she will show you how she can track the volcanic flooding in terms of area, thickness, and volume, and assess the volume impact crater size frequency distribution, because you can track that. You can just create impact crater size frequency distribution variations that show you what the frequency distribution should be as a function of time. And we're evaluating this in terms of highland flooding, cryptomaury, and applying this actually to intercrater plains on Mercury. Very interesting possibilities. So in conclusion, the LRO mission, absolutely fantastic. And of course, the laser altimeter data have just changed our whole perception about the moon, as have many of the other instrument data. We've been able to do impact crater size frequency distribution, buried impact crater morphometry, flooding experiments, slopes at all scales. And these, again, can be tested with other data that's being collected at the same time. And a key thing here, you need to think about the future, because within a couple of months, GRAIL will be launched, and we will actually be able to use these new understandings of the distribution of this material to look at the high-resolution gravity data and compare it to these observations that are going to be obtained by GRAIL. So it's an exciting time, great data from LRO, and we can look to the future as GRAIL begins to test some of these ideas and utilize this data to get at the structure of the crust and the mantle. Thank you very much. I can repeat the question if you want.
Okay. As you know, there's
Possibly even answer it, I'm not sure. But
as you know, there's little of any correlation with samples, at least between age and composition of marble salt. It's feeble. But you have this situation in Oriental where you see the location of the flooding is correlated with time. Is there any correlation then?
Okay, so you heard Carly describe the moon mineralogy mapper data, and we're actually, if you look at Jenny's paper, she describes and discusses that. But of course, we really need to go back with the new data that's coming out and reassess that. So we can look at the volumes and their placement as a function of time, and they're very, very broad correlations. But the spots are very small and the volumes are very small. So even those correlations, you know, there's just not enough to make any significant conclusions, I would say, at the present time. But we're going to relook at that with the new, possibly Z-level data as it comes along here. It's a very good question. Mike?
Yeah, Jim, you've really shown how effective it can be when you combine multiple data sets. And you've indicated that GRAIL is a potential next step for additional insight. Are there others that you would like to add to further provide detail and insight?
Well, I think, you know, this is the kind of thing that really, if we just back one talk to what Mark talked about, all the insight that's coming from LROC and detail. You know, we're talking about all these variations, and now we can go down and look at the actual outcrops, okay, and see what's going on. So, you know, when you go into the interior of Euler Crater, for example, which is in the Imbrium Basin, you can see a stack of hundreds of meters of lava flows. And, you know, if we had the spectral resolution, we need one more instrument, one more spacecraft, that is a very high spatial and spectral resolution spectrometer, okay, that can get in there and really look at that sort of thing. That would be ideal. So we've got a lot of data, and we can look at these things and start correlating them, and the color data that Mark's talking about will be excellent to start that. And then if we can really work in with the spectrometer data at high spatial and spectral resolution, you know, building on InCube, we could just, it would be great. So we're looking for all the data we can get. Thank you.